Hello, Mr. Claudia here, and today we're going to continue learning all the fundamentals of curve sketching. Today we have a really new concept, the idea of concavity and points of inflection. So up till now we've learned how to know if a function is increasing or decreasing and where it reaches a max min point, which are all things you can see by looking at a graph. But consider if I had 2 points, so point A and point B, and I wanted to connect them with a curve. Well, there are two ways to draw this curve. There's kind of this upward path where it bends up, and there's this downward path where the curve bends down. This is the idea of concavity. It's the bend in a curve. This first one that I drew here where it bends up, this is called concave down. One way to know it's concave down is the cave faces down. Another way to think about it is it's frowning. You've heard probably the word concave when you looked at lenses in science. So concave is that bend, and then there's that cave side, and then, like I said, the cave is facing down. Conversely, this one here, this bend is concave. That cave is facing up, so it's concave up. And you could think of this as smiling. So some of these ideas, like when you think about a parabola, you can have a concave down or a concave up parabola. So let's just go over this kind of new definition and talk about concavity over this weird curve we have here. So let's look at one step at a time. So we have a curve here. Okay, so here the cave is facing down. So this portion is, let me use a black pen. This portion is concave down. And then from this point on, it's facing upward. It's concave up. And so we'll write concave up. Here it's all facing up again, so this is another interval that is concave up. Okay, then there's some sort of asymptote. From this point onward, the cave is facing downward. Oh, and then it changes here. So this is a concave down section. And then from D onward, we're always facing up. And even though this graph is going to go on forever, it's always going to have that concavity that's facing upward. So that's an important kind of idea, concave up. So concavity is something you can see from the graph. There's no real trick to what concavity is. It just looks up or faces up or faces down. Now these points where you switch from facing up to facing down, or concave up to concave down, these are called points of inflection. Or POI. So there's a point of inflection here, and you can kind of when you draw it, it's kind of fun, right? It's going down and then it changes the way it bends. Over here, there's another POI, point of inflection. What about here? So here I am concave up, and then I change concavity and I'm concave down. But there can't be a point of inflection here because there is no point. Like if you think about it, the function doesn't exist here. It's an asymptote. So there is actually no POI here because f at c, so the original function at c, does not exist. So that's a point we're going to get to. And what about this point here? Well, this point we have a concave up, and here we have concave up. So there's no change of concavity, so this is no POI. So right here, no POI, because there's no change in concavity. So there's a definition of point of inflection, or POI, the point where the curve changes from concave up to concave down, or concave down to concave up. And that's the important definition. So let's just think about, like, before we look at how to do this, let's just think about what concavity means. Move this up here. Let's say you have a parabola from grade 10. So I'm going to draw a nice concave up parabola. This is a concave up parabola. So think about what is happening here. If I were to draw a tangent line here, what's the slope of this tangent line? Well, it's a negative slope, so therefore the derivative at this point is less than 0, right? It's a negative slope, negative derivative. And then here, if I drew a tangent line here, well, we know that this is a horizontal tangent line, so the derivative is, the slope is 0, so the derivative is 0 too. And what about here? Well, if I drew a tangent line here, it's an increase, it's a positive slope, so this is a derivative that's greater than 0. So essentially what's happening, remember, this whole thing is concave up. We're not talking about increasing, decreasing, and min points right now. We're talking about concavity, and the whole thing is concave up. What concave up really means is that the derivative, the first derivative, is increasing, because the derivative starts off as negative, it becomes 0, and then it becomes positive. So you can think about it, if you can draw that instantaneous rate of change, or the instantaneous slope, it's starting off as a really big negative number. It's getting smaller, closer and closer to 0. So it's a small negative number, becomes 0, and then now it's getting to be a bigger and bigger positive number. So the entire time, my derivative is increasing. The entire time, my slope of my tangent line is increasing. So I'm just going to write that here. That's the conceptual way of explaining concave up, or the calculus way of explaining concave up. The slope of the tangent line is increasing. Or another way of saying this is the derivative is increasing. Now, similarly, if I have a function that is concave down, we'll take a really simple function, a simple parabola. The whole thing is concave down. We have the same sort of situation. If I were to draw the slope here, the slope starts off as positive, so the derivative is greater than 0. Then I have a horizontal tangent line, so that would be where the derivative is equal to 0. And then I have a negative derivative here. So in this case, for concave down, it really means that the slope of the tangent line is decreasing. Oops. Or the derivative is decreasing. Once again, here's the derivative. It's very, very steep positive. It's a large positive number. It's getting smaller and smaller and smaller and smaller, closer and closer and closer to 0. It gets to 0, and now it's -1, -2, -3, and it's getting more and more negative. This is the calculus explanation of concavity, and this is going to come really useful for the last section in this chapter, where we do some IB-specific problems. So they really like you to be able to understand this idea. Finally, let's just look at what a point of inflection is. So if I just draw a nice kind of point of inflection, so it would be right here. Remember, here I have concave up, and here I have concave down. And this is a POI. And if you want to think about it, here I have a slope that is positive, 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 getting a lot smaller. And then here it starts getting bigger again. So, so a POI is a change in concavity. Therefore, derivative changes from increasing to decreasing, or vice versa. So in this case, we're seeing the increasing derivative and then a decreasing derivative, or the other way around. And that's really what's happening at point of inflection. So in practical sense, how are we going to deal with concavity inflection? Well, let's look at it. Now what we're really looking at is the change in the derivative. So we're actually going to be using the second derivative to do this, the derivative of the derivative. And that's where we get our test for concavity. It's written down here. This is kind of like a lesson, the last two lessons combined, because we're actually going to do the points and concavity in the same lesson. So to the test for concavity, if the second derivative is greater than 0, then the function is concave up. If the second derivative is less than 0, then the function is concave down. Again, you kind of saw that here, right? The slope of the tangent line is increasing. The derivative of the derivative is positive. Concave up. One way I remember this is if it's positive, the second derivative is positive, you're happy, so it's opening up. If it's negative, you're sad, so it's opening down. If the function is defined and the second derivative changes signs, then there's a point of inflection, and that's what we've been talking about. Concavity changes. So let's do some examples that'll help us understand what's going on here. Oh, actually, I just want to talk about this a bit more. IB really stresses this one kind of point about the second derivative. They say a second derivative, or sorry, a POI will only occur if the second derivative is equal to 0 and concavity changes signs. We say that these are both necessary conditions. It's not sufficient to just have one or to just have the other. You have to have both. And to show you an example of why this could be a problem, we're going to do an example actually later, but I do like to put it here in the lesson just so you don't miss it. You get a function like this, which looks like a parabola, but actually you can have a function like y equals x to the 4. So it's actually a quartic function with a few double roots. So this point here so the second derivative at c equals 0, but no change in concavity. Therefore, no POI. So that's an important thing here. This is concave up, and this is concave up. So if you found that the second derivative is 0 here, which you would, that's not enough to say it's a point of inflection. You have to look at the change in concavity as well. So we're going to look at that in one of our examples. On top of that, technically, you can have a situation where the second derivative does not exist and the concavity changes sign. And I put that here. You can still have a POI if there's a second derivative that doesn't exist and the concavity changes sign. An example of that would be similar to what we did in the last lesson, vertical tangent function. So something like this. And this is C here. So here I have f double prime at c does not exist. Because of the vertical tangent, you have the second derivative doesn't exist here. So but you do go from concave up to concave down. So f double prime at c does not exist, and change in concavity happens. So therefore, POI. An example of this would be y equals x to the 3rd. Now, like I said last time, this is not in IB. So you don't need to know this, but you're going to need to know it when you get to university and look at this. So I just want to make sure your notes are correct. So this is not an IBSL, it's in the HL course. So you can have a situation where the second derivative equals 0 and the concavity changes sign. That's a POI. You can technically have a POI also where the second derivative does not exist and the concavity changes sign. However, all of the functions that have situations like this, we don't see them in IBSL. So for all intents and purposes for our course, for the IB math exams, you're never going to have a situation where you can have a POI at the second derivative if the second derivative doesn't exist. So you can assume that the second derivative has to be 0 for there to be a point of inflection. Either way, when you get into university and you move on with your math career, either way, you just have to make sure that you have the second derivative equals 0, a second derivative doesn't exist, and this change in concavity. So really the big unifying thing is that there has to be a change in concavity from up to down or from down to up. So that's a little aside there. Whew, okay, again, this point really comes up a lot. They might give you a very short question where you have to know this idea, these two necessary conditions. Okay, finally, the wait is over. Let's do some real practice questions. So let's start with number A here. So find concavity and the points of inflection. Okay, so when we're talking about concavity, we're talking about the second derivative. So right off the bat, when you see these words, concavity, I'm going to just underline in red, concavity and points of inflection, this is telling you find the second derivative. So even if you don't remember anything from this lesson, those words should be a big hint to you. So let me write this function out. And now let's start deriving. Drive carefully. 3x squared minus 6x plus 4. So that's the first derivative. Oh, I love polynomial functions. They're so quick. Now let me find the second derivative, which is just the derivative of the derivative. So 6x minus 6. Okay, now I have the derivative, or second derivative. Now I have to look at the sign. Remember, if it's positive up, I know it's concave up. If this is positive, it's concave up. If it's negative, it's concave down. So really, I'm doing the same strategy I did in the last few lessons. I need to find these so-called, and I put this in brackets, like critical points. We don't call them critical points. I call them possible POIs. So to find the possible POIs, we have to set the second derivative equal to 0. Same strategy as we did last time. So I have 0 is equal to 6x minus 6. Now remember, the easiest way to do this, well, I need to solve this, but the best thing to do is to factor. And from the factored form, I find that x is equal to 1. Okay, now, I think I showed you how to do questions like this. You probably don't need to think too hard to make a sign diagram. You're going to look at the sign of, in this case, the second derivative. My possible point of inflection is 1. So now I need to look at the sign of the second derivative. I can do this with a table. Can also do it by inspection, right? Let's use a table. Come on, we don't want to. This is confusing enough, this lesson, if we don't have to worry about new strategies. So let's just do this the old-fashioned way. Okay, so we have x is less than 1, x is greater than 1. My factors are 6 and x minus 1. Okay, let's look at what happens here. So I have 6, it's always positive. A number that's less than 1, like negative 2, this is going to become negative, this is going to be positive. So this is going to be negative and positive, negative and positive. Great, I have my sign diagram. Now I can figure out a lot of things from my sign diagram. Therefore, f at x is concave up if x is greater than 1, right? Because here the second derivative is positive. And it's concave down for x is less than 1, right, in this region here. Now, this point here is a point where where the second derivative is 0, could be a POI, but we also have to check the change in sign. Well, because I go from negative to positive, or positive to negative, this is a POI. So I'm going to write that as well. And there is a point of inflection at x equals 1. Oops. Muy bueno. So far, so good. So really, this whole lesson, it's a new concept, but the technique is almost identical to what we did in the last 2 lessons. So that's why I find the curve sketching, it's a difficult concept, but the algorithm for solving the problems is very predictable. Just in terms of space management, we're going to skip down to question C here. So we have y, in this case, y is equal to x to the 4. I told you this was going to be a weirder one. I kind of showed you an example up above. So y is equal to x4. If I want to find the concavity and points of inflection, I need the second derivative. I'm going to write it out in this other format, Leibniz notation. So dy dx is equal to 4x cubed. And then I need the second derivative. So I'm going to write d squared y over dx squared. That's the second derivative. And this is going to be 12x squared. Now, to find the possible POIs, we set d squared y over dx squared equal to 0. I set the second derivative equal to 0. So I have 0 is equal to 12x squared. And so from that, x has to be 0. Oops, sorry, you can't see that. There we go. Okay, so let's continue doing what we did last time. I'm going to draw my sign diagram, very similar. This is a diagram showing me the sign of the second derivative. Oh, shoot, I should write it like I did. D squared y over dx squared. Oh, so messy. Okay, and once again, just so I don't get too confused by this whole lesson, I'm going to draw a table. So I have here x is less than 0, x is greater than 0. My factors were 12 and x squared. No matter what number I put, I'm always going to get positive, right? 12 is always positive. X squared, something squared is always positive. This is always positive. So this is positive, positive. So there is this weird case. And this case, remember, is in IB. This is the one that's up here. This is in IB. Just because I have a spot where the second derivative is equal to 0, that doesn't mean it's a POI. I have to also look at concavity. And because the concavity is from positive to positive, therefore, there is no POI. So f at x is concave up for x is greater than 0 and x is less than 0. And there is no POI. There's no point of inflection. So that is a case that we need to be aware of. And just, if you know, it's not the hardest thing, but just be aware of it. Okay, let's make a big new page here to do our last example. So this is section 8.3, page 3. And let's do question B. And question B is y is equal to x over x squared plus 1. And we see that, we're very sad because it is a rational function, so we know it's going to be a tough derivative. Now, remember, we're finding the second derivative. If we're looking for concavity and points of inflection, so immediately we should just be looking for the second derivative. So let's start. Let's find the first derivative. I'm going to use this notation, y prime. Remember, that's another way we can write the derivative. And I need to use, unfortunately, the quotient rule. So let's take the derivative of the top thing, which is 1. And then times the bottom thing, minus the top thing, times the derivative of the bottom thing, which is just 2x. And then that's all over the derivative squared. So far, so good. Now I'm going to clean this up a little bit because I need to do another derivative, and it's really confusing and messy right now. So this is going to become x squared plus 1 minus 2x squared over x squared plus 1 all squared. And I can even do a subtraction here, and I get negative x squared plus 1 over x squared plus 1 all squared. So that's probably the simplest I'm going to get it. So now I am going to find the second derivative. Here we go. I need to again use quotient rule. So the derivative of the top thing, which is, what's the derivative of this? Negative 2x times the bottom thing, which is x squared plus 1 squared. Remember, the nice thing about calculus is it follows rules. So Even though this is messy, just for now, follow the rules of applying all your differentiation rules. Subtract the top thing, which is negative x squared plus 1, times the derivative of the bottom thing. Now, oh my god, this is a chain rule question. Just when you thought you would never have to worry about chain rule again. Remember, the derivative of this denominator here, okay, well, the derivative of something to the power of 2 is 2 times that something to the power of 1 times the derivative of the something, which is derivative of x squared plus 1, which is just 2x. So one of your nightmares is back. That's the chain rule. And that's all over, don't forget, this is a quotient rule, this is all over x squared plus 1 all squared, and then that whole thing is squared. And then you breathe a big sigh of relief because you finished the calculus, right? You finished finding the derivative. Now is the cleanup. Remember, what you're trying to do is get to a situation where the second derivative is factored, because then you can analyze the signs. So I need to factor this. Now, there's a lot of different ways you can clean this up and factor it. One way is you could just straight expand everything. So you could expand this, expand that, just keep going and do some subtractions and then factor. That's a lot of work. What's really useful about the second derivative of a rational function is you're going to see some things that are repeated a few times. And here I see it. X squared plus 1, x squared plus 1, x squared plus 1. So there is a common factor right here, x squared plus 1, that I should be able to take out of each term. So I'm going to clean it up a little bit first, but I'm going to leave the x squared plus 1s intact. And this is kind of a strategy. So let's, x squared plus 1, let's leave that. This is negative x squared plus 1, so this is not an x squared plus 1, so you can do whatever with this. Let's leave it for now. Oops. This I can clean up a little bit, so 2 times 2x is going to be 4x. And then I have x squared plus 1 to the power of 1. Remember, with chain rule, all these things are multiplied, so I can move them around in different orders, like they're all just factors. And then the denominator is going to be x squared plus 1. Now this square, this 2 and 2, they multiply. That's an exponent rule, so I get x squared plus 1 to the power of 4, which actually is not so bad now. Okay, now remember my trick here, and this is a trick that that is a nice thing, the one saving grace about the quotient rule for the second derivative. You can factor out x squared plus 1. Actually, I can also factor out an x from the numerator, and I can factor out the number 2 from the numerator. So I'm going to factor out 2x x squared plus 1. Now what's left over? Well, okay, if I factor out those things, I'm left with a negative, and then this, if I take x squared plus 1 to the power of 2 and I divide out one of those, I'm left still with x squared plus 1. Then I have minus x squared plus 1. I've divided out a 2x, so I'm left with 2, and the x squared plus 1, I've divided that out, so actually that's it. That's everything. And the denominator is still x squared plus 1 to the power of 4. So I'm just going to write here that I factor the numerator. Now, the great thing here is that, look, this is to the power of 1 technically. This is to the power of 4. So these I can divide out. And this is why we spent so much time doing exponent laws, because now you end up with x squared plus 1 and x squared plus 1 divide out. So I have 2x. This whole thing is, well, let's just write this out and then I'll figure it out. Well, I don't like all these negatives here. It really kind of bothers me. So I'm going to multiply the negative in. So I get negative x squared minus 1. This is going to be negative. So it's going to be plus x squared. Negative times 2, so let's do it this way. Minus negative 2x squared plus 2. I'm going to multiply that 2 in first. Just do it one step at a time. And this becomes x squared plus 1 to the power of 3 because we divide that out. Let's finish solving this. Look at this. We have some factors now. I'm just going to clean this up a little bit. So I have 2x. I have negative x squared minus 1 minus minus, which is plus 2x squared, minus plus, which is minus 2. X squared plus 1 to the power of 3. And finally, so I end up with 2x negative x squared plus 2x squared. So that's x squared minus 1 minus 2 minus 3 over x squared plus 1. And it was a bit of a nightmare. Whoa, a bit of a nightmare, but we finally did it. We got the second derivative into a factored form. Remember, this was one of our least favorite things to do when we did questions like this in the derivatives chapter. This is a lot of work. Often in an IB exam, because this question would take so long, often, but not always, you might just be given the second derivative. So you might actually get a question like this, and you're given this point. And you should remember, if we have the second derivative, the next step is to draw the sign diagram. Where are we going to do this? Why don't I go up to the top of the page here, just so we have a bit more space. Well, sorry, the next step is to find the possible POIs. So let's go up here. So for possible POIs, remember, they're not called critical points. I would set the second derivative, it was y double prime, is equal to 0. So I have 0 is equal to 2x times x squared minus 3 over x squared plus 1 to the power of 3. However, there's that other point, that other option too, which is to set the second or where is it? Find the points where the second derivative does not exist. In other words, we set denominator equal to 0. So in this case, it would be x squared plus 1 to the power of 3 is equal to 0. So those are the two cases I need to do to find the possible POIs. Which one you want to do first? Well, let's do this. So if I cross multiply, I get 0 is equal to 2x x squared minus 3. Now, whether the factor, well, for this to be true, x is equal to 0. That's one of the cases. The other option that would make this 0 would be if x squared minus 3 is equal to 0, which is x squared is equal to 3, which is x is equal to plus or minus the square root of 3. Very important. Remember, if you take the square root, if you want to undo that square and take the square root of 3, you have two possibilities, a positive and a negative. They'll both give you positive 3. Oh, sorry, they'll both, yes, they'll both give you positive 3. So those are some possible POIs. Technically, there's a possible POI here. We know in IB it's not going to be a POI, but we still need this point for my sign diagram. So how do I undo this cube here? Well, I take the cube root of both sides. So I end up with x squared plus 1 is equal to 0. Bring the 1 to the other side. Okay, well, there's no solution here because you can't take the square root of a negative number. So in this case, it wasn't, it didn't lead anywhere. Okay, so now that I have my possible POIs, I'm going to draw the sign diagram. Remember, this is the whole point of it. This helps me know if I'm looking at a positive concavity or negative concavity. So this is the sign of y double prime. I know I wrote f prime, but we've been calling it y double prime in this question. And the points that I have are going to stress you out a little bit. They're negative root third, 0, and positive root third. Now, don't worry too much about those numbers. You'll find out it's not going to be the worst thing in the world. To solve this question, I'm going to use a table, and there are 1, 2, 3, 4 intervals I'm going to try to squeeze in here, and there are quite a few factors, so I'll try to make a long table. 2, 3, oh boy, space management, not always the best. Okay, so now I have x is less than the root 3. I have negative root 3, x is between negative root 3 and 0. x is between 0 and root 3, x is greater than root 3. And then I have to put all my factors in. Well, my factors are 2x, x squared minus 3, x squared plus 1 cubed. We don't care if it's in the numerator or denominator. They are all factors. Okay, now we're looking at signs. So remember, root 3 stresses us out. What is root 3? Well, if you forget, and you will forget, so it doesn't really matter, you know it's going to be a negative number, 1 point something. I mean, what's root 3? I always forget. It's 1.73. Oh, actually, in this case, it's negative 1.73. So really, to be safe, choose a number that's really, really negative. Negative 10, right? Like, who cares? If I choose negative 10, this is going to be positive. Negative 10 is negative. Okay, negative 10 squared is 100. Minus 3, still positive. And, okay, negative 10 squared is 100. Plus 1 is 101. Cubed it, it's positive. So you can think it through. Now here, this one's a little trickier. Between 0 and negative root 3. Well, I know that it has to be negative root 3 is bigger than negative 1. So if I choose negative 1, that's a safe bet. So this is going to be positive, negative. Negative 1 squared is 1, minus 3 is negative. Negative 1 squared is 1, plus 1 is 2, squared is positive. In fact, this one is always going to be positive because I'm squaring whatever number I have. Actually, this will always be positive because 2 is always positive. Okay, choose a number between 0 and root 3. There's some symmetry here. I'm going to choose the number 1. This is positive. 1 squared, this is negative. And I'm going to choose a number bigger than root 3, say 5. This is going to be positive. 5 squared is 25 minus. This is also positive. So now, remember, we can count the number of negative signs to determine if it's going to be positive or negative. I have 1 negative sign here, so it's negative. 2 here, positive. Negative and positive. Oh, cool. Let me fill in my sign diagram. Negative plus negative plus. So there we have it. We can figure it out. Therefore, f of x is concave up between negative root 3 and 0, and x is greater than root 3. F of x, oh, it was not f of x, it was y, but that's okay. Concave down for x is less than negative root 3, and x is between 0 and positive root 3. Now we're not done there. We also are interested in the POIs. Well, here we go from negative to positive, so this is a POI. Here we go from positive to negative. This is also a POI then. And negative to positive, this is also a POI. So there's a POI, x is equal to negative root 3, x is equal to 0, and x is equal to positive root 3. Oh, sorry, let me just put that up there. Now I know what you're thinking, what a funny little graph. Like, what does this look like? It's so weird. It has 3 POIs, it has negative, plus, it's a rational function. Again, we're getting to that. By the end of this chapter, you'll be able to graph this entire function. But if you're, getting impatient and you really want to spoil the surprise, I can take out my GDC. Let me go to the graphing mode. Let me just graph it, show you what it looks like. So there's the function there. So if you guys could see, which you can't, apparently. Tab. Okay, we can't see anything. X divided by bracket X. Oh, you can do it. You can turn on the light. Like that. There it is. Ha! X squared plus 1. Let's see what it looks like. Neato. Let me zoom in a little bit. Menu, zoom, settings. I'll just change the Y coordinates to be a little bit tighter. So how about negative 2 to 2? Hopefully you remember how to do that. There's the function. Isn't it cool? So you can kind of see what's happening here. We have a concave down section at negative root 3, so negative 1.7. We go from concave down to, all of a sudden, concave up. and then we're, so there's a point of inflection there. We're concave up, and then at 0, we have another point of inflection where we're no longer concave up, we're now concave down for a while, and then at positive 1.73, it changes to concave up again. So what a cool function. And again, we'll be able to comfortably graph this by the time we get to the end of this chapter. Do you want me to just do a little sketch there? Sure. So let's do it like this. So it goes like this. Neato. So we have a POI. We have a POI, and we have a POI. Remember, the POIs aren't ever at the max and min points. They're where it changes the shape. The max and min points, how do we find those out? Refer back to your previous lessons. Okay, that's it for today. That's a lot to digest. Our homework is page 236, number 1 to 8. And I put cryptically in my notes here from previous years, think hard about number 8. Well, as if you weren't thinking hard about all the questions. Anyways, good luck with that, and I'll see you next time.